Okay, my computer kicked off and I actually erased my board. So I've kind of recreated. Let me pick up where I was. We'd figured out what R and big R and little r are. Big R here is, if I call this y is equal to c, is always going to be c minus g of x, because this is my g of x, and little r is always c minus f of x. And so since this goes down here to b, my volume here would be pi from b to a, c minus g of x squared minus c minus f of x squared. By the way, don't try and get fancy and say, oh, because there's c in both of there, I can ignore it. No, you can't, because you're squaring it, and it actually makes a big difference. Now, let me just generalize. Ultimately, every time we do a volume problem, it's actually going to be this. It's going to be big radius minus little radius squared. If you can figure out what the big and little radiuses are, you can do these problems. You say, well, we didn't use the little radius before. Well, actually we did, you just didn't know it. When we had a problem where we had it, say, touching the x-axis, and we're revolving around the x-axis, my big radius is actually my f of x. My little radius is actually 0, because there's no radius there to cut out. And if you look at that and plug that back in, it's really rx squared minus 0 squared. Okay, now, there is one other type of problem that will pop up in this section, and I want to hit it, and then we'll be done. This is disk method part 2, or maybe I should say part B. What happens if we are going around the y-axis? We've done something like this with areas. But let's just take this problem. Let's say we had f of x is x squared. In fact, I'm going to write it y is equal to x squared. Y is equal to 0. X is equal to 2. But we're going to go around the y-axis. Well, if we draw a picture of what we've got, y equals x squared looks like this. X equals 2 is over here. By the way, this is going to be important. This is 2 comma 4. And that is my y is equal to 0. So there's my boundaries. And we're taking this area, but we're revolving it around the y-axis. How are we going to do that? I do it by changing all my variables. I do y is equal to x squared. Change this to x squared is equal to y, so x is plus or minus the square root of y, but in this case, because it's positive, it's the square root of y. Excuse me. Boy, I messed that up. This would be x is equal to y squared. Square root of x is equal to y plus or minus, or y is the square root of x, right? And then everything else changes. But what I would do right now is kind of sketch this in. Y is equal to x squared looks like that. Well, what is this value here? Well, on this graph, this was 2 comma 4, so this becomes 4 comma 2. Y is equal to 0 becomes x is equal to 0. And it's basically this region revolved around here. Now, if you look at that, this region and this region would be exactly the same. If I was to pick this up and put it right here, I would get the same value exactly. But what I am doing is I am actually taking this it's this region, but now I can think of this being revolved around the x-axis. That's what I wanted to do. So it's that revolved around the x-axis. This shape right here around the y-axis is the same as this shape around the x-axis. So I changed everything. I changed my x and my y at the point. I changed the x and y at the axis. So y0 becomes x0. X equals 2 actually becomes x equals 4 because that was a point of intersection, and y becomes square root of x. And this then would be pi from 4 to 0. My big radius is this line, which is 2. So big radius, because we're revolving around now the x-axis, big radius is 2. And my little radius is this one, which is square root of x squared, dx. And if we do that, we will get the volume for this. So I know that was a little confusing, so I don't want you to be confused. So let me just try it more general. We have some shape, I don't care what it is. Let's say instead of that, it was this right here. And we're going to revolve it around the y-axis. So it's this area around the y-axis. This line was y is equal to 0. This is x equals a. This point is a comma b. And this is y is equal to some value of x. Let's say this is square root of x. What we're going to do is redraw this picture, essentially, where we're going to think about this shape being revolved around the x-axis. And so it would be a shape that would look like this around the x-axis. This y0 becomes x0. This point AB becomes b comma a. This is y is equal to a. This line right here, y is equal to a. And this we have to take, and I'm going to do it with the y is equal to square root of x. We're going to exchange the variables. X is equal to square root of y, or y is equal to x squared. And that would be then this right here. And then when we would integrate it, we would be thinking about this revolving around this axis. So this would be pi from instead of from a to 0, in this case, would be from b to 0, and we would have a squared minus, in this case, x squared dx. So a little tricky, but it's similar to what we had done on areas where we took and turned things around. So, all right, that is it for that. There's one more section called shell method. It's something that hasn't been taught in calculus for the last few years, at least in AB calculus. And they've added it this year. In fact, they've added it this year probably means it'll be on the AP test. So we'll cover that in the next set of videos. All right, these problems that have the rest of this, you should be trying problems 27 through 37. 27 through 37 odd, this second part, again, out of section 7.3. Oops, I said I wasn't going to write in red anymore, but better change that. 27 to 37 odd in that section. All right, that's it for this lesson.